Hi everyone. So it's 1:03 and we'll begin now. Okay. So this is the third class in the USACO Bronze class, and it's about sorting and time complexity. So first of all, I hope you guys did your homework yesterday, and I hope you find the practice problems helpful. It's just the more practice you do, obviously the better you'll get at it and the easier it will be for you. And then yeah, you can hopefully pass USACO Bronze after practicing. Okay. So let's just start with sorting and time complexity. So the first thing we're going to go over is time complexity. What is it? So time complexity is just something that tells us how efficient our program is, and later we'll see that it tells us whether our program will run within the limit of the problem. So for USACO, the time limit for Java and Python is 4 seconds. For C++, it's 2 seconds. That's because it's faster, so it can do the same number of operations in a lower time. So time complexity represents how many, like it's a representation of how many operations our program can do based on the size of its input. Like if you double the input, how will the running time be affected? That's what time complexity tells us. So if you guys don't know what an operation is, well, an operation is just a singular calculation or process. Like for example, addition or subtraction or one iteration of the loop or reading some input, those all count as one operation. So how is it actually represented? We use something called big O notation. And this is just like, we just have the letter O, and then inside parentheses, we have some function of n, which tells us how our program will behave with certain values of the input. Like if we have, also one thing to note is that when we use big O notation, we ignore constants. So if we have n plus 5,000, this is still O of n, because the reason for this is because we're looking how our running time changes, not the exact running time. So our running time will change linearly according to how much data is put into it. So O of n plus 5,000 is still linear, and we just write it as the simplest possible form, which is O of n. Okay, and also remember that n is just the size of our input. A lot of times in USACO problems, you'll see that there are some values represented by n, but that's not necessarily what I mean here. For example, in one of the problems yesterday, cal gymnastics, we had the number k, and that was also included in our time complexity, and if we actually evaluated it, which we can do later. So as I explained earlier, O of n means that our running time increases linearly with respect to our input. So if our program took 500 milliseconds to run with 5,000 inputs, and then it'll take 1,000 milliseconds or approximately 1,000 milliseconds to run with 10,000 inputs. So O of n is just one common time complexity. Others include like O of n times log n, O of n squared, O of log n, O of n to the n cubed, n to the whatever power, also 2 to the n sometimes if you're going through like subsets. Okay, now we've talked about what time complexity is. Now let's talk about how we calculate it. The first thing we do is we break our code into chunks. So these are standalone loops or method calls or declarations like you see in this code below. So once we have our chunks, we can analyze what the time complexity of that one chunk is. So for below, what we have is we just have 3 lines of code, each of which is declaring a variable, and the third one has one operation. So all of these are what is known as constant time, or O of 1. And that's because even if you had, let's say we had another number n that we were reading in down below and we were doing some operations with it, this code will always run, or like, let's say that we were reading in input. Instead of int z or int y is equal to 6, we had int y is equal to sc or scanner.nextInt. Then we're just reading in that input. The time it takes to read in that value, to read in that singular value or declare one variable is going to be constant no matter how many things we have to read in, right? So that's why it's constant time. Okay, so here are some other things that we have to look out for in time complexity. If we have loops, for example, then our time complexity of the loop is just how many iterations we're going to have to go through. So if we have a for loop going from x equals 0, x is less than n, and the increment is just 1, we're just going to have n iterations because we go from x equals 0 all the way up to x is n minus 1. So those are n total iterations of the loop. So that's why it's O of n. And even if it was, let's say that, yeah, I'm going to ask you guys this question. What would happen if we did, instead of the increment for our loop was x plus plus, what if it was x plus equals 2? So instead of each time going up by 1, we increase x by 2. So how would that change your time complexity? What do you guys think? Could you guys put that in chat? Okay, so maybe my explanation wasn't clear enough. So when we have time complexity, we're talking about how our running time grows with respect to how much data we put in. So if we put in twice the amount of data, we should expect, if it's linear, if we put in twice the amount of data, we should expect 2 times growth in running time. So what happens in this loop, even if we decreased, yeah, the complexity is O of n. So yeah, someone put O of n over 2, and yeah, you're heading in the right direction because that's how many iterations of the loop there are. But the thing with time complexity is that we just get rid of all the constants. So if you multiplied n by 1/2, or you multiplied by 2, or multiplied by any constant, or added or subtracted anything, we don't consider that in the actual big O notation. We just worry about the constants. So it's still going to be O of n because even if we're going through half the number of iterations, even if we double the data, we're still going to double our running time. So let's say that right now we have going through our loop n times is taking us 500 milliseconds, for example. If we did x plus equals 2, or we made our increment doubled, that would mean we have half the number of iterations of our loop, right? Because we double the increment, so we're going to get to our final value twice as fast. So we have half the number of iterations. So our running time should decrease. Then, if we increased n, so we increased our bound again, then what's going to happen is we're going to go twice as far. We have twice the amount of data. So since this is linear, or we're just going to increase the running time by 2 again. It's just going to be twice the amount of iterations. So our running time is going to double. Yeah, so the code below this first loop is another loop, except we're going from x equals 0 to x is less than n plus 5,000. This is still O of n because remember, we just ignore all constants. Except for like powers. Those are not constants. Those actually matter. So yeah, you see here, we have some code that is O of n squared. So this is another rule about calculating time complexity. If we have nested loops, what we do is we multiply the time complexities. Because for each iteration of the outer loop, you're going to make some more iterations of the inner loop. And if the inner loop goes n times and your outer loop goes n times, you're going to iterate n times, and you're going to do each of those n times. So n times n is n squared. You're going to have n squared total iterations. So that's going to be the final complexity of our loops here. So even though this is n plus 5,000, you could really write this as the outer loop iterates n times, the inner loop iterates n plus 5,000 times. If you multiply those, you get n squared plus 5,000 n. But when we were multiplying, we can also, in our big O notation, we can get rid of the 5,000 because that's the big thing here. We get rid of all the constants. We just care about the n's and how they grow. So this is in reality just n squared code. Okay. And even if we didn't have n on the inside, if we had k, we would write the complexity as O of n times k. That's what's seen here if we had nested loops. Yeah, so those are like the 3 basic rules for time complexity. If you just have declarations or simple operations, it's going to be constant time. If you have loops, it's just the number of iterations of the loops without constant factors. And then if you have nested loops or nested statements, you're just going to multiply the time complexities of those. All right, so now that we've isolated the chunks of the time complexities, what happens if we put it together? Like what happens if we had a nested loop And then we also had just a regular loop that goes through n times. We're going to take, as you'll see in a second, we're only going to take the maximum complexity. So on the next slide, there's an example. So over here on the top, we have n times k. We have an O of n loop as the outer loop and an O of k loop as the inner loop. So the total complexity of that is O of n times k. Then in the bottom loop, we have O of n on the outside, O of n on the inside. So the total complexity is O of n squared. But if we're trying to take the maximum of these, we can't really compare them because we don't know the comparison between n and k. So we're just going to add those together. So it becomes O of n squared plus nk. But what if we had one that was significantly bigger than the other one? So the first loop right here is a nested loop, and it's O of n squared, as we've seen before. The second one is just one loop, and it's O of n. O of n squared is a lot bigger than O of n. Like if you had 1,000 elements, O of n squared would be approximately 1,000,000 operations, while O of n would just be like 1,000 operations. So if you add those two together, you're going to get 1,000,000 and 1,000 operations, which in reality is just close to 1,000,000 because of the scale of the numbers we're dealing with. So we just call this as O of n squared. We don't worry about any of the lower order complexities that we have. So that's the other big thing for time complexity. We just look at the largest complexity we have, and that's going to be our complexity for the entire code. And of course, if you have cases where you can't really compare the complexities, you're just going to add those two together because they're still going to add up to a significant amount of operations. Okay, so why does all this complexity matter? As I've said before, it tells us if our code will run in time, but let's talk about concretely how. So while this isn't really a problem in bronze problems, in all bronze problems, there are some that you might have to worry about this, as we'll see in a second. And in order to tell if our code will run in time for USACO, like 4 seconds in Java, we've got to make sure that our number of operations is less than 10 to the 8th. So this is just like something that you can tell by if you tried testing it out, if you just kept increasing the number of operations that Java had to do until you get to 10 to the 8th, you would get pretty close to 4 seconds. This bound is kind of it's kind of loose. Like you could probably get away with going above 10 to the 8th operations, but the thing is that you might also have some constant factors. Like in time complexity, we ignore constant factors, but those might play a role in the operations. It's just we ignore them so we can only focus on how the running time grows. But yeah, so 10 to the 8th is a pretty good bound for how many operations you should be aiming for in order to run in time. And this can tell you which algorithm you should focus on. And it's really relevant in higher divisions like silver, gold, and platinum. So here's an example. So this is a bronze problem where there's an array. We're going to read in an array basically, and the size of the array can be up to 10 to the 5th. So if we did some complete search algorithm that, for example, maybe was n squared, if we did an O of n squared algorithm, we would at least have 10 to the 5th squared operations, which is 10 to the 10th operations. So that is above our bound of 10 to the 8th. So that tells us that that algorithm will not work for this problem, and we'll have to think of something else. Let's actually go over that problem right now. So here's a link to that problem. I'll put it in the chat. But first, I want to check, does anyone have any questions? I don't see anything in the Q&A, but in general, do you guys have questions? Okay, I'm not seeing any questions, so I'll just go ahead and we'll go over the problems. Okay, so this problem is called sleeping in class. What happens is Bessie is excited to return to in-person learning, but her instructor is very boring, so she ends up falling asleep in class. So she's been sleeping in class, and another student wants to make it seem like she's been sleeping a lot more than she actually has, like more consistently. So what she's going to do, she has a list of how long she's fallen asleep in class, and that's the array we're going to be reading in. What she wants to do is she wants to make operations that combine adjacent elements of the array. So for example, if this was how long she slept in class, 1, 2, 3, 4, 5, then she can combine the log to make it look like she actually slept for 5 minutes, or no, for a time period of 5 total in the second and third classes combined. So she wants to make all of these values consistent. So she wants to make the entire array equal to some number. And she wants to find out what is the minimum number of operations she has to do to get it this way. So let's look at the sample input. So the first one, we have 1, 2, 3, 1, 1, 1. That's how long she slept in class. So what is the minimum number of operations she can use to make the entries all equal? Well, one thing she can do is make all the entries equal to 3. She can combine this 1 and 2 and make that a 3. She can leave the second 3 alone, and then she can combine the last three 1s and make that into a single 3. And that'll make all the values in the array 3. And that in total took 1 operation to combine 1 and 2, took 1 to combine 1 and 1, and took 1 more to combine all of these. So that's 3 total operations, and that's the minimum amount. So for the second one, there's no way, the only way to make all the elements in the array equal, or all the elements, is by only making it so that there's one element in the array. So combining all the elements. So that'll take 2 operations. And then in the third test case, all the elements are already equal, so we don't have to do anything. That's why it's 0. Okay, so now let's think about how we can solve this. So one thing we can do, one idea, is that you could go through each number, and since you want to make all the elements in the array equal, right? You could go through each number in the array, and you could try setting all the other elements to equal that element. So that could be your common value, the element you're looking at. So there's one problem with this. Do you guys know what the problem with that is? The problem with this strategy of picking one element from the array and then making all the other elements equal to that. But we have to check all the elements to do that. So what's the problem here? I'll give you guys a second to think about that. Okay, so the problem with this is that we want to choose one element to make to be the one that's equal. So like you want to choose one element that's a common value, and that common value can be any of the elements in the array. So all 10 to the 5th elements could possibly be that common value. So there you go. You've already got a runtime of O of n to find which element is a common value. And then after that, you have to check all the other elements, whether you can make them that common value. So to do that, you're going to have to go through the entire array again, which is another O of n running time. So if you combine those two, this is really a nested loop, right? So if you combine those two, you're going to get an O of n squared running time, which is exactly what we said we cannot have in the last slide right here. Okay, so this O of n squared algorithm won't work. So is there anything else that we can possibly use to help us combine them, but not in O of n squared time? Can anyone make any observations about this? Anything at all that they see? So one thing that I notice is that every time you combine elements, you're going to keep the sum of those two elements equal, right? Or you're going to keep the sum of those two elements because when you combine them, you add them together. So you're not getting rid of any numbers, you're not adding any numbers. So every time you combine, something that's going to stay equal is the sum of the entire array. You're not introducing any new elements, you're not taking anything away. So all the numbers in the array must keep their sum, or the entire sum of the array must be equal. So that's one thing. Another thing is that if we want to make all the elements equal, then the sum must be divisible by the number of elements, right? And it must be equal to the number of elements times the value of those elements. So because that's just the sum of the array if they're all equal. So knowing those two things, we know that the number of elements we must have has to be divisible, or no, the sum of the elements must be divisible by the number of elements we have, and the sum also has to be divisible by the common value. So what we can do is we can iterate over the size of our final array, and we can use the fact that the sum won't be divisible by every single element. It's only going to be divisible by a few. And if you're unsure about how many exactly, we can actually check this. So let me open an IDE and we can write some code that can test this. So what we want to test is how many numbers, or no, what is the maximum number of divisors of any number from 0 through our maximum n, which in this case was 10 to the 5th. In order to do that, first what we're going to do is have an outer loop that goes through the numbers from 1 all the way to 10 to the 5th. So yeah, you can also write 1e5 instead of having to type out the zeros. It makes it a bit easier. So yeah, and then we're gonna find the number of divisors of these of each one. And the easiest way to do this is just go from 1 to that divisor and count the number if if the number you're looking at mod your divisor is equal to 0. So I'll keep a count of that too. And then we also want to update our answer at the end. So if the number of divisors we found was greater, then we're going to increase it. So, and then let's just print out our answer. Uh-oh, let's see. This is a time limit exceeded. Yeah, so this is n squared code, and it's using n to the 10 to the 5th or 10 to the 10th operations, which is not okay. So I actually ran this on my Eclipse earlier, and it did give me an answer. It gave me the answer. Let's see. So it gave me 128 earlier. So that tells me that over all the numbers from 1 to 10 to the 5th, the maximum number of divisors a single number has is 128. So let's say we checked all those 128 numbers to see whether they will work for this problem. And then for each one, we're also gonna check all the numbers in the original array. So if we do that, our total running, like the total number of operations is gonna be 128 times 10 to the 5th, which is around like 10 to the 7th, which is definitely less than 10 to the 8th. So this will definitely work and run in time. And now we're going to actually implement this. And let me share my IDE. Okay. So can you guys see my IDE now? No? Okay. It says participants can now see your screen. Okay, now yes, there we go. Okay, so the first thing we're gonna do, as always, is create our scanner. So you'll notice that this problem is February 2022. So that means we can actually submit using system.out. Yeah, great. Now you can see my screen. So you can submit using a system.out, so you don't have to read and write to a file. All right. Okay. And then the next thing we're going to do is this problem actually had some test cases. So what that means is we have our actual problem where we have n, we read in n and we read in the array and then we print out the output. But each of those is a test case, right? And each test case in USACO has some more test cases. So we have to read in the number of test cases for that. So I'll make a variable for that. Then we'll make a loop going from 0 to the test case. So basically just iterating over the test cases. All right, and then now we can actually solve our actual problem. So the first thing we do is read in n. And then after that, we read in our array. So I'll just call it r. No, I can call it sleep. And I forgot my brackets. All right, and then let's read it in. So I do for, and I have for loop going from 0 to n. And I'll say sleep bracket x is equal to in.next int. So that just reads in our array. Right now, what we're going to do is we want to iterate over the size of our final array. So our size starts at the total, like the total value of the array, total size of the array, which is at first n. And then, first thing, oh yeah, I forgot. We remember that our sum is kept constant, right? So we should actually find our sum because it's an important value in this question. So we can just update our sum here. All right, now that we've done that, we can iterate over the size of our final array. So I'm actually going to do a decreasing for loop here. So I'm going to start at n, and then I'm going to go up to 1. So x is greater than 0, and we're going to decrease. And the first thing I need to check is that if I actually iterated from 0 through n all the way, what I'm going to get is an n squared algorithm, which we just said doesn't work. So the first thing I need to do is check that this sum is divisible by the new size of our array. So if it's not, we can just break. So not break, we can continue, go to the next case. So if sum mod x is not equal to 0, we're going to continue. So that's the keyword that you use to make our loop go to the next iteration without executing the rest of the code. Okay, so otherwise, if our sum is actually divisible, we can actually test this and see if we can make all the elements equal to sum over x. Because remember, our total sum is sum, and then the number of elements we have is x, so all the elements must have a value equal to sum over x, right? Okay. In order to do that, what we're going to do is create a new array. And this one is going to have size x because this is what we're testing. We're testing if our new array can have size x. And what I'm going to do is I'm going to start filling in this new array with numbers from my old array. So maybe it's best if I show this on a whiteboard. Let me pull that up. Okay. So now what we have So this was our old array. I'll use the input that we had last time. 1, 2, 3, 1, 1, 1. So that was our old array, right? And now we're going to create a new array. And let's say we're testing an array of size 3. So that means we want 3 elements. The sum of the original array was 9. Sum of the original array was 9. And since our new array has size 3, we want all the elements to be equal to 3, right? Because 9 divided by 3 is 3. If we have 9 total sum and 3 elements, all of those elements are going to have value 3. So what we're going to do is we're going to start from the beginning of the original array. And we're going to add, so initially all our values are 0, right? Forgot to tell you, because that's the Java original value. And what we're going to do is we're going to add these elements until we hit a sum of 3. So we can add this 1 over here, and now the 0 becomes a 1. It's a 1 now. All right, but 1 is still less than 3. So we're not going to go on to the next element yet. But let's just move on to 2 in our original array. So now I'm going to add 2 to this 1. And now this 1 is a 3. So now this is satisfied. Now I can move on to the next element. So now I can add 3 over here, right? So if I do that, the 0 becomes a 3, and 3 is exactly what I wanted. So now I move on. And then these next 3 ones, I'm going to add all 3 of them. And it's obviously going to be in 3 separate steps, but I'm just showing it in one. So that's great and all, but what if we overshoot? Like, what if this actually doesn't work? And instead of having, let's see, instead of having this 3 over here, or no, instead of having this 2 over here, we instead had a 3. What would that look like? So this value is a 3. What would happen? So this doesn't actually work. So let's just get rid of this last one. So what's going to happen is you're still going to have this 1, and you're going to add it to this 0 right here. So the 0 becomes a 1. Okay, since 1 is less than 3, we're not done yet. So we're going to add the next element of our original array to this 1. So this 1 now becomes a 4. So here's the problem. All our elements in the original array was positive. So we can only increase values in our new array. But if the value in our new array is already greater than our target, we're never going to reach our target. We're only going to continue increasing. So right here, we can already tell that this does not work. So this is what we were testing for. If we can actually add all the numbers in the original array to get a consistent, like all the numbers in the new array equal. So this is how we're going to tell if it doesn't work. Okay. So that's the explanation for why that works. And now let's go back to the code. So now we've already decided the new size of our array. And what we're going to do is set this first pointer. So I'm going to call it cur. And it's initially pointing to the first element in the new array. Then what I'm going to do is I'm going to iterate over the elements in my old array. So I'm going to go from y equals 0 up to n. And once I do that, I'm going to first check if the element in my new array at the index I'm talking about, so new array of cur, if that value is less than my target value for the sum, which is sum over x. If it's less, then I'm going to add that the value from my old array, which is array of x, or no, array of cur, or no, array of y, sorry. And I'm going to add that to new array of cur because that's the index that I'm looking at in the new array. So I'm going to do new array of cur plus equals array of y. And I actually called it sleep, not array. Okay. So now that I've added sleep of y to new array of cur, now I need to check, is new array of cur too large? So if it is, I know that I'm never going to decrease new array of occur. I'm never going to go back to my target. So that means this whole process does not work. So if new array of occur is greater than sum over x, we're just going to stop this because it doesn't work. And to do that, we're just going to break from this inner loop. Otherwise, if the sum is still less, then we're going to keep going with the same one. But if the sum is exactly equal to our target sum, so if new array of occur is equal to our target sum, which is sum over x, we're going to move on because we're done with this value in the new array, and we're going to move on. So we're going to do cur plus plus. And this should work because let's say that the sum was less than the target sum, then this if statement is not going to converge to anything. We're not going to do anything. So we're just going to repeat in this loop. We're still staying at index cur. So we're going to continue increasing that until we get to a target sum. All right, at the end, we're going to test whether all the elements in new array are already equal. So in order to do that, we can simply do that by just testing the last value. Because if the last value is equal to the sum, then we know that all the other ones must be equal to the sum. And we know that because if the other values were not equal to the sum, then we've already broken out of our loop over here. So it just suffices to check if our last value is equal. So if new array of the size is now x, so the last index is x minus 1. So new array of x minus 1 is equal to our target sum. That means we've done it, and that's our answer. Because this is the minimum, this is like, in order to get the minimum number of operations, we want the maximum size. Because each operation that we combine two numbers, we decrease the size of our array by 1. So if we find some array that works, then we know that is the best possible array. Because if we try anything smaller, it's only going to take us more operations to get that array. So this is going to be our final answer, and we can just print it out right here. We're going to print out the number of operations it took us to get to this new array. And that value is n minus x, because we started with an array of size n, and we decreased it all the way down to an array of size x. So the operations to get there is n minus x. All right, and then we can break because we're done. We already finished this test case. And let's test if this works on the sample cases. So let's run this. And these were the sample cases. And the output is what it's supposed to be, 3, 2, 0. Took 3 operations in the first one, 2 in the second one, and 0 in the third one. All right, so does anyone have any questions over how we, over just the problem in general? You can also leave it in the Q&A if you want. Okay, so I don't see any questions right now, so we're just going to move on. So the next thing we're going to cover is sorting. All right. Sorting. So what is sorting? Sorting is just arranging items in a certain order. And in USACO, you'll normally see arranging words and numbers. And what we mean, but usually the certain order will be like the natural ordering of the numbers. So you'll have just, if you had a sorted, like if you had 5, let me write it out. If we had some list like 5, 9, 2, 3, 2, 4, 1. Then in order to sort this list, we're going to end up with 1, 2, 4, 5, 9. So that's the natural ordering of these elements in non-decreasing order. And there are a bunch of algorithms to sort the numbers efficiently, not just numbers, also words. There are, yeah, just to sort arrays efficiently, but there are a few that are widely used. So we're going to cover those today. So one is called bubble sort. And this is an O of n squared algorithm where at each iteration of the loop, we're always going to move the largest element of, or the next largest element of the array to the correct spot. So I'm going to explain that on whiteboard. So let's say that we actually had these numbers, 5, 9, 2, 4, and 1, and we were trying to sort this array. What would bubble sort do? So it starts with 5, 9, 2, 4, 1. What it's going to do is it's going to start from the beginning, and it's at each step, it's going to compare two values. It's going to compare the value you're currently looking at and the next value. And if those two values are out of order, meaning that the one on the left is greater than the one on the right, then we're going to swap these two. So for 5 and 9, they look good. 5 is less than 9, so that's the correct order. Then we're going to go to 9 and 2. So 9 and 2 is actually not good. So 2 should go back here. 9 should go up here. So far, our new array is 5. Then we swap the 2 and the 9. We have a 2 over here. But once we bring the 9 over here, so the 9 is right here right now, then we're going to compare this 9 and 4. 9 is still greater than 4, right? So this 9 has to swap with the 4. So the 4 is going to come over here, and the 9 is going to be right here. After that, we have a 9 and a 1. 9 is still greater than 1, so we're going to swap this 1 and a 9. So 1 is over here, and 9 is over here. So this is what bubble sort will look like after one pass, one iteration of the outer loop. It's not completely done yet, but this is on the way for sorting. So it's going to be 1 and 9. On the next pass, we're going to do a similar thing. And notice that the greatest element in the array, 9, is already at its correct spot at the end. Let's do it one more time. So we have 5 and 2. Those are not in correct order. 2 should be here, and we swap that, and we get 5 over here. So since 5 is over here, we compare that with 4. 4 should be swapped with 5. So 4 goes over here, 5 goes over here. Then we compare 5 and 1. 1 is less than 5, so 1 goes over here. And 5 goes over here. Then we compare 5 and 9, and those two are in order, so we don't do anything. And now look, the second greatest element of the array, 5, is in its correct spot. So that's the thing with bubble sort. At each step of the array, we're going to move the next greatest element to its correct spot. All right, so I had a question that says, do other programming languages also call it bubble sort too? So it's not actually called bubble sort in a language or anything. This is just the concept of bubble sort. And it's not really like when they implement sorting in programming languages, they don't use like a specific type of sort. They don't use merge or bubble, or they don't use anything like that. They have their own special optimized sorting algorithm. Okay. So the next pass is going to look like this. So 2 and 4 are already in the correct order. 1 and 4 should swap. So it's going to be 2, 1, 4. And then the rest are in order. So since the last 3 elements were already in order here, we don't have to worry about those. So we can just worry about these two. 1 and 2 are not in order, so we swap them. So it goes 1, 2, 4, 5, 9. And there we go. We've now sorted the array. So the only problem with this is that we took so long. We took n squared time. If you looked at that array in the previous problem, we didn't have to sort it, but it was still a large array. It was 10 to the 5th in size. So if we tried sorting that, it would take 10 to the 10th operations, which is really long, and you can't even sort that in USACO. So instead, sorting in programming languages uses optimized sorts, but here's the actual time complexity for sorting algorithms that's actually good. It's n log n. And I'm going to explain one n log n sort, which is good. It's called merge sort. So here's how merge sort works. So what happens in merge sort is you start with the big array. You start with 5, 9, 2, 4, 1. What you're going to do at each step, you're going to split the array in half. So I know it's not an even number, but you're going to split it approximately in half. So you can do 3 on one side, 2 on the other. So let's split it into 2 arrays. So we have 5, 9, 2 over here. And we have 4 and 1. So the eventual logic of merge sort is to split the array into 2 parts. Then you're going to sort both of the parts using another merge sort. So it's actually recursion. So you're going to sort both parts. Then once you have both sorted halves, you can put them together in sorted order in linear time. So in n time. and that's less than n log n and n squared, so it's pretty good. So the log n factor comes from all the splitting in two, and you'll see that happen pretty often. Like in binary search, you also split in two. So those are algorithms where we split into two, and that's where you get the log factor. So what I said that we're going to split in half and then sort, right? So we're going to keep doing that. We do it recursively, so we keep calling it. So now we're going to sort this array 5, 9, 2 using merge sort. We're going to split it into two arrays again. We have 5, 9, and then we have 2. So now we're going to sort 5 and 9 actually, and we're going to call merge sort again. So we split it into two arrays again. And now they're just singular numbers, 5 and 9. So after we do that, we're going to combine these two in order. And they were actually already combined in order, but just for the sake of like showing all the steps, I'm going to show this too. So now that they're corrected in the connected in the right order. All right, and then the 2 was on the right half of this branch, right? So now we're going to combine it back with this 5 and 9. So 2 is already sorted because it's just one number. 5 and 9 is already sorted. So we can do this, we can combine this in linear time. It's not like that important to know, well, I guess all you have to do is you have to start a pointer at the beginning of each array, and you take the lowest number at each step and combine them together. That's how you combine the array. So now you have 2, 5, 9. All right, so now we're going to call merge sort on this right half before we finish the sort. So we break it up into 4 and 1. And those two are already sorted. So we're going to combine these two again in the correct order. So it's 1 and 4. And then now we have the two halves of the array are already sorted. So now we combine them. And that also takes linear time. So it's going to be 1, 2, 4, 5, 9. And that's our sorted array. And this sort works in n log n time. So it's pretty good. And that's the time complexity for actual sorting algorithms. And even when we use them in USACO, like USACO has, or Java has some built-in methods called arrays.sort and collection.sort. And these two methods are optimized methods. They're not like direct applications of bubble sort or merge sort. They are a bit more complicated and work faster sometimes. So that's collections.sort. Collections.sort is really fast. It's like better than merge sort, and it's still n log n, but it's optimized. But arrays.sort, so here's the thing in Java. So arrays.sort, if you use it on primitive data types like ints and longs, then you're going to end up with, you can end up with a worst case complexity of O of n squared. And you do not want that because sometimes it can take too long. But in USACO Bronze, you usually have enough time to do O of n, like not O of n squared, but quicksort, which is used in Java. So if you use arrays.sort in Java or in USACO, it's fine. But sometimes other contests like code forces or higher divisions in USACO, you can't use arrays.sort. So you could, your options are to either use a different language, like I recommend C++ because that one's O of n log n. You could also use something called wrapper classes, which puts these ints and longs, those primitive data types, inside objects, which are then used, they use at merge sort on those objects, so it's faster. Or you could use collections.sort. But here's the thing, to use collections.sort, you've got to use something called an array list. So array lists are actually pretty good. They're basically like arrays, but their size and elements can be changed. But in arrays, you can also change the elements, but you can't change the size. In an array, once you declare it, you always have the same size. But an array list is not a regular array. So it's an object too. So this is how you declare it, and this is the syntax for array list. You can declare your array list, and this is a syntax to add numbers to your array list. It adds numbers to the end. So in this case, it'll add 5 to the end. You can also delete elements from your array list, and this is the method to do that. But when you're deleting, be careful. If you delete from some element in the middle, you're going to end up with an O of n squared algorithm, because what happens is you have to shift all the numbers that were after the number you deleted back. So that's going to take O of n time, because you're going to have to go through the entire length of your array list, which has a size of n. All right. And then you can also, this is the method to set a certain element of the array list. So these methods are like what you use instead of using bracket notation like we did with just regular arrays. All right, and there's one last problem I want to go over before this class ends, and it's called kayaking, and it's on the topic of sorting. So this problem is actually on code forces and not on USACO. So I'll copy paste this problem into the chat. And let's go to this problem now. So here's the problem statement. So we have someone who wants a kayak and he wants to join a kayak group. And what they're going to do is there's 2N people and they want to have N-1 tandem kayaks. So there's going to be 2 people in those kayaks and there's going to be 2 other people who go on single kayaks. And what you want to do is you want to adjust, like you want to put people in the right kayaks so that the kayaks don't crash or they don't fall over. In order to do that, you need to minimize the difference between the weights, and they call it the instability. So what you're basically trying to do is find a way to find, like, you're going to find an arrangement such that there are 2 people in each of the N-1 tandem kayaks, and there's some, like the difference between the weights of the people on the kayaks, the sum of all those differences is minimum. That's what the instability is. Okay, that explanation might have sounded confusing actually. So yeah, I'll just, you're gonna find the difference between the weights of the people on tandem kayaks. And then you're gonna add up all those differences, right? And that's gonna be your total instability. And you wanna minimize this number. So one thing that you can notice is that, let's say just I have some numbers. So let's work with 59241 again. So I have 59241. Let's say that these were the people that I was putting on tandem kayaks. I'll actually add one more. I'll add 3. 3 would go here in the sorted array. If I want to arrange these people into the tandem kayaks such that the differences between their weights is least, what I'm going to have to do is I'm going to have to sort them, and I'm going to have to use the difference between consecutive people. Because however you look at it, let's look at this guy who has weight 1. Well, this guy's going to be paired up with another guy, and the instability of those 2 people is going to be the difference between them, right? So if you have a difference between 2 and 1, that's going to be less than the difference between anyone else, between 4 and 1, between 9 and 1, obviously because they're farther away from 1. So the observation you have to make is that you always want to pair up people that have consecutive weights in the sorted array. In order to get the sorted array, we need to use a sorting algorithm. And that's what we're going to be displaying here, the Java arrays.sort algorithm. So let's write the code for this. And I'll go to my IDE to do that. Okay. So first thing we're going to do, as usual, is make a scanner. And also, Codeforces has similar time limits to USACO, and it uses standard input and output. Okay. Now what we can do is we can read in our n. So n is equal to in.next int. After that, we can read in our array. So it's going to be, I'll just call it R. And I can read that in with a for loop. So now that my input is read in, what I can do is I can sort the array, because I'm not always going to get a sorted array. Like the second example, we have a mixed up array. So in order to sort it, oh yeah, actually, right, I forgot one thing. So we're not actually going to sort it in the beginning, because remember, we still have those 2 people who are in single kayaks, not the tandems. So in order to find, we're just going to complete search this. Our n is small enough that if we do an n squared or n cubed algorithm, it's going to work. And we're going to search all the pairs that are going to go on the single kayaks. So when we do that, we're just going to ignore those two people. So since choosing pairs of people from a set is n squared, and then going through the rest of the people's n, we're going to have a total of n cubed algorithm. So we can make a for loop, an outer for loop to go through our first person. And then we're going to make another for loop to go through our second person. So it's going to start from x plus 1 and go to the end of the array. And also, we have two n numbers to read in here. So let me fix this. So n times equals 2. That should fix it. All right. So now that those two people have been selected, what we're going to do is we're going to make a new array with all the people in our tandem kayak. So it looks like we're not going to have enough time to finish this today, but I'll still post the solution to this problem on the website. And then, yeah, you guys will be able to look at it. So the homework for today that I want you guys to do is this USACO problem, which, let me share my screen, and you'll be able to see it. It's also going to be in the PowerPoint, so if you look at that, that's fine too. So the homework is, why did the cow cross the road 3, which is this USACO problem, and you can find the link on the PowerPoint. So that's all I have for today. So thanks for attending the class, and I'll now hand it over to the next presenter. Okay. All right, now you're a co-host, Vishal.
Is my microphone working? I can't hear. Sorry. Let me change my audio settings. Wait, Arnon, can you say something or?
Hello. Can you
hear? Oh yeah, okay, I can hear that. All right, never mind. We're good. Okay, so like last time, I'll give like a 4 or 5 minute break. So at like 2:05, we can come back. Most likely next lesson.